who actually was one of the participants maybe like 6 months ago.
Something like that.
Yeah, and we asked him to give a talk 6 months later. Here we are. And I'll give you a very brief introduction to Yao-Lun. So he did his Ph.D. in University of Texas at Austin, and now working at RIKEN, one of the really big universities in Japan, and at the Star and Planet Formation Lab. Also, when he's not doing science, apparently Yao-Lun is actually roasting coffee, which he started recently. So if whoever's interested in science or coffee, please feel to
Please teach me.
Yeah. Right. And before we start the lecture, I want to remind everyone to sign up here. And even on the next slide, you can see, can we go? Yeah. You make sure to sign up. This is just to make sure that just in case somebody managed to get COVID, we want to inform everyone else. And try to keep your mask on if you're not eating and drinking. Otherwise, I mean, it's much bit more relaxed. Right. Thank you so much, Yao-Lun, for coming today.
Sure.
Yeah.
All right.
Let's start.
Okay. Let me one moment. All right. And my drinks. Very sorry. Okay. Should I use the mic?
Sure. You can
Alright.
remove it.
Okay, cool. All right. All right. Well, thanks to Lena for introduction. This is really great to be here. I was in Tokyo. So today is really my pleasure to kind of share some of the new things that actually happened in the field of astronomy in the last year or so, and also ongoing. And I'm just going to focus on like one area of that. But hopefully we'll get you excited about this new coming instrument telescope that we have. So let me dive in. So as astronomers, we're always looking forward to understand how do we come here as how do human begin, how does Earth begin. So the biggest wondering I guess to drive us to do astronomy is to understand how do we come here? Like how does everything happen? How does solar system form? How do Earth form? How do life actually begin? So I mean, this is just like very schematic, like cartoonish picture to show basically the organic matter in our Earth actually evolved through a very long time, like through here it's like 2.5 billion years, but it comes a long way to get to this part where we have organic matters can function. I can talk to you, and so we want to look back into the time to see, okay, how does these organic matters coming from? And the next closest place we can go into is to look for other bodies in our solar system. And this time we want to look into the bodies that actually contain perhaps the pristine material, the material that in our solar system is not being altered. So a good candidates are mostly comet and some asteroids that contain those like pristine materials, sort of like leftover, those like dust and gas left over from the formation process of our solar system. So this is an image taken by the Rosetta mission by ESA a couple of years ago, and this is a mission actually going into the comet and actually orbiting the comet and actually land a lander on the comet to actually do a very close by in situ observation. So this mission gives us wonderful data about telling us about organic matters, what's their composition, what's the dust property, gas properties in a comet, and can help us to inform what's the ancient solar system going to look like. And kind of here so this is sort of the gallery they come up with. Like, I'm not expecting you to read anything. I don't even know what they are for some of them. They are just too chemistry for me. But then I think the point here is that we see all kinds of different class or types of molecules. There are some molecules a little bit smelly, like those like sulfur-bearing molecules. There are some poisonous molecules, So those are organic molecules we will see in any chemistry classes and or even in high school chemistry. We know those molecules, and we also see that in comet, which is like basically when the solar system is formed. So at least we can date our chemical origin back to the point when the solar system is formed. And kind of close to Japan, there's a really incredible mission. It's called Hayabusa 2. They actually go to an asteroid called Rikyu, and then they kind of touch down and kind of just like kiss the asteroid and take some sample out of that. So this is a movie showing that process. And they actually return this canister of like asteroid material and drop it in the ocean, I think somewhere close to Australia, and to retrieve it so they can bring it back to the lab to analyze it. And they actually found out there's also quite a few organic matter here in this asteroid. So this is very important data set, and also measurements can really help us to ground like the formation history and chemical evolution history of our solar system. So if we go a little bit backward to see, okay, where's the beginning? Where's the beginning of these chemical journeys that like leads to, the beginning of life, basically. So we have to go also look into how does the star actually born and how is it related to the planet formation. So just briefly, like a kind of a journey of star formation starting with like, a blob of a gas and dust, sort of like our cloud, and then the gravity starts to take over in the center. And you can imagine everything just kind of collapse to the center. And then you have the stars forming, and oftentimes it will drive the outflow, whatever. It'll kind of look like this. This is obviously a very simplified version. And a lot of the material got dispersed over time, and then you left with like a disk. And you can imagine like the planets in our solar system, but instead of a planet, they kind of is like a continuous or semi-continuous matter, like orbiting around a newly formed star. And eventually everything kind of settled down, planets are formed, you have a nice planetary system, and hopefully there will be life beginning in here. And so we'll start to look into those systems, like we kind of go one step back from the planetary system, which is like our solar system we know, and we kind of want to go back in time to see what's the chemistry actually look like at those stages. So in planets, so now this is also pretty recent result, I think in the last 5 or 10 years. We now know that those disks actually have a lot of structures like this, and this is a sort of one of the best studied disks that actually we think there's a planets actually in the cavity of the disk, and so we can actually use radio telescope to go in to look at those disks and find out there's a bunch of different molecules in there. Those are a little bit larger molecules. So you have a couple of carbons, you have some nitrogens. And also that they're not the morphology of how they distribute doesn't look exactly the same from one to each other. So through modeling those molecule distribution, you can tell us quite a bit about what's the chemistry actually look like in those systems. And we can also take a step even backward in time to look at a protostar when the disk hasn't even formed yet. Again, using radio telescope. And this is really iconic example as this source is called IRIS 16293-2422b. There won't be a quiz about this later, but we focus on this source. We actually see, like this is a spectrum we took. There's crazy like peaks you can see here, and can zoom in and zoom in. You still see a lot of we call it emission line here, and basically each line represents a particular signature of a particular molecules. So through these lines, we can already identify like there's very abundant organic matters already at the beginning, like when the star just formed, not just when the planetary system formed. We already have really complex chemistry when a star is formed. And interestingly, if we kind of look into the baby star environments that I just showed you slides ago, and compared to what we got from the comet 67P, which is the Rosetta mission that I mentioned before, and we just compare the abundance. So here it's basically plotting the abundance versus abundance. So it's like composition of different molecules. Each point here is showing a particular species and how that related to entire total kind of gas matters. And they kind of fall into this kind of one-to-one like a line here. So suggesting that, okay, we have a comet which is pristine material from our solar system. We have a very distant young baby star, and they somehow have very similar chemical composition. They basically made of similar gas. So I think this is very striking and also somewhat surprising result, but it actually hints that there may be a chemical link, like for what we have in our solar system could already be dated already back to when the stars formed, just like emphasis, reiterate what I said before. And so how does the chemistry actually occur when a star is formed? So here I want to kind of pivot a little bit to a different phases. So I have been talking about gas for quite a few slides, but I would like to say that the ice is actually where all things happen. So what happened is that this is my star model, like proto-star model. You have a star in the center, which is not shown yet. But it's basically a star giving out radiation. So you have warm in the center and kind of cold in the outskirts. So let me zoom in. You have a star forming, and outside your temperature kind of drops. So when the temperature drops low enough, your gas starts to fall, like frozen out. You basically like a snow. Your water vapor started frozen out to form a lot of ice, and that's actually where most of the chemical reaction actually happens. So this is a movie showing what happened on the dusty grain. You can imagine it's like the soot or tiny little powder of dust grain, and this is kind of movie illustrating how the molecules actually frozen out onto the dust grain. So you have a different molecules, different atoms. So I think so you can. This is a water molecules basically growing, and you start to have kind of icy surface building up, and in the end your dust grain covered with like a thick ice mantle, where basically all of the gas lock into this like frozen surface, and that's really useful because in interstellar environment the density is really low. So if it's just gas and gas, the chance they're meeting each other to have a reaction is pretty low. But if you have a place which is ice mantle, they lock every kind of a different gas on top of it, then the chance they can react with each other is tremendously higher, and that's enable a lot of the chemical reactions and forming different molecules on those icy surface. So what typically happens is that you have a very complex molecule that can form on the ice. So here, just like you have different functional group. This is a little bit chemistry, but you have different functional group like attach onto each other, and then they form larger molecules. It is still on the ice though, so it is only when those dust grain travel into the inner hotter regions where ice being sublimated. Temperature is high, your ice is gone, and so that these molecules are in gas phase, and that's typically it's very easy to detect those gas phase molecules with radio telescope. So these are the emission line that I showed you a couple slides ago. But like a lot of the action is actually happening in the ice, and where we don't really see from those radio telescope that we often use. So detecting ice is really, really tricky, and we often cannot see them directly. So how do we see them? So the way, and it's a very kind of well-established way to detect ice is through through absorption. And how it works is that this is a water molecules. If it's a gas phase water molecules, these molecules can fly around, can rotate, can do whatever things they have, because they're in gas. They're really free. But if these molecules lock into the same place, all it can do is vibrate. Its bond will just vibrate, and like that. And so to enable this vibration, it takes energy. So the water molecule you need to give it energy and kind of like shake it around, and it will just vibrate. So when there's a radiation coming from your nearby star, for example, the radiation will come in, and these radiation contain energy and will shake up these molecules, and therefore that part of energy is being taken away from this radiation. When we observe it, you say, well, there's some radiation is missing, and we can infer that, okay, that's because there's a water ice molecule that is vibrating, taking away part of energy in this stellar radiation I'm expecting. So we can infer the existence of ice through absorption spectrum. And so this is what it looks like actually in reality. So this is absorption spectrum. You can see there's a lot of dips here. Each of them kind of correspond to different molecules. So common ones like water here, carbon monoxide, methanol, ammonia, carbon dioxide. So these are the common molecules that we can see, and we have been using all kinds of different telescopes to try to see them. And fortunately, also unfortunately, most of these features are in infrared wavelength. So this is in 3 to 20 microns, and I think there's some molecules absorption is a slightly shorter wavelength, but they're mostly in the infrared wavelength. And detecting infrared wavelength is very difficult because from the ground, because our atmosphere is really good at really opaque in terms of infrared light. That's why we have greenhouse effect, for example. Traditionally, this kind of observation has been done through a space telescope, like space-based telescope, so that we don't no longer have this opaque atmosphere in infrared wavelength. So recently, there's a new telescope being launched a couple years ago. I think it's about 1.5 years ago or something like that. It's called James Webb Space Telescope, and often we short it with JWST. And this is really a it transcends all of our previous knowledge about the arrival of this telescope actually helped us to explore something we never thought about we can explore before. And I'm going to tell you why in the remaining of my talk, basically. So before I do that, why we want, what's infrared actually do in order to help us to understand the universe? So showing on the left here is a visible light picture of a pillar of creation. So this is really iconic Hubble image, and you can see there's a lot of dark stuff, and that's because there's a lot of dust blocking the light from the background starlight. But we also want to know what's inside the dust, how does those dust distributes, and by switching to infrared light, you can see that we can now see through most of the dust. We can still see some structure here, but it basically enables us to kind of peer into where the star is forming, where the ice and gas is kind of collapsing onto each other. And so we built this telescope, not I, but NASA and other, and ESA and also a Canadian Space Agency. They're all coming together to bring this, to build this telescope. It's called JWST. And the goal for this telescope is we want to have an infrared telescope that is powerful enough and have a very good resolution and sensitivity so that we can see through those very opaque region that we cannot see through in visible lights. So this is what a mirror looks like, and it's like a very open concept. It doesn't really have like a cone or something, because it is sitting out a very dark universe, outside of outside of our Earth orbit. So it doesn't really have that cone, but also another constraint that it has is that if you build a cone telescope, there's no launching vehicle, there's no rocket you can take that much of a payload onto in the space. And just as a comparison, the JWST mirror is about 6.5 meter. It's about like a school bus, like a bus size. But Hubble is only 2.4, so this is a really big difference. You can see this person here is as a scale, and so because we want to, obviously we don't want to point our really sensitive telescope directly into the sun, but also sun heat up the stuff. So a lot of heat signature will be seen in infrared. So we want to avoid the sun as much as possible, and that's why we actually sent this telescope to a million miles away. It's about 1.6 million kilometers away, and have this telescope kind of always facing outward, away from the sun, and so you kind of rotate in this particular point in the Earth and Sun and Moon system called L2, but it's basically kind of stabilize it and can just do a dance around here for the next 10 or 20 years. So finally, in the Christmas in 2021, this telescope, the rocket carrying this telescope launched. This is just as a kind of reference point. The mission concept is first conceived in 1989. So this is a 30 years journey to actually build this telescope from start to think about it, actually make it happen, actually launch it. And this is really I think this is morning Christmas time in the United States. So I was watching this with my wife, and this is just really pivotal point in my career as an astronomer, actually. And we also have a little bit surprise when watching the launching it. This is a final view, actual real-time image movie of James Webb leaving its launching vehicle. departing for its final journey. And you can see there's some, I think this is some solar panel or something like that. You can see there's a lot of covering around that. And in the moment you will see, this is obviously the Earth. In the moment you can see that it actually opened its solar panel, and which is really vital actually, because now it doesn't have any launching vehicle support. It has to be powered by itself. So if this solar panel opening is failed, then the entire mission kind of just gone. Yeah, I don't know how long this will take. But when I was watching it, just I'm not even expecting this. I'm not expecting to actually see, having an image of this telescope here. Yeah, and you can also see there's some lighting here. That's because this launching vehicle actually propelled itself away from the James Webb so that it doesn't really collide each other. So now you can see the solar panel is opening. And then I think this is sort of the last, we're waving a goodbye to the telescope and hope for the best at the time. Because from this moment, there's still a 6-month traveling time for the telescope to go to the L2 when it is orbiting. And I think there's another, it's about 1.5 months to actually go there. And there's 6 months of testing to make sure everything actually works as we expected. So there's still a long way to go from this point. This is December 25th in 2021. So how does this telescope actually perform? So here showing a very iconic view of part of the interstellar medium. This is called, some people call it cosmic cliff, but this is part of a bubble in the Carina Nebula. And this is an image taken by Hubble. I mean, you already see a really nice landscape here. Some stars, kind of a lot of structure here. But here's what we see with JWST. You can just see that we kind of remove all of those opaque matter around it and see intricate structure here. There's some white stuff here. That's probably some bubble, kind of radiation blown other materials away from a newly formed massive star. There's some filamentary structure. Just a lot of things here that we just never noted before because we don't really have the capability to obtain this kind of image. There's also another example, but this is a single protostar. So this is a protostar is forming, and there's driving its bipolar outflow that I told you about. This is an image taken by a Spitzer Space Telescope. This is probably around 2010, 2012, and this is what we get from JWST. And this is we never know there will be some sort of filamentary structure in this outflow cavity. You can also see there's some dark line here. That's because there's a disk is forming, and disk is really, really dense. So if we see edge on, you just you couldn't see through. So that's why there's dark line here. But I mean, this is just these kind of images a piece of cake for this new telescope. So but the previous image, we have to really pushing the limits of our instrument to get those kind of image. So we really, right now, we're just scratching the surface of the capability that we can do with these new telescopes. And astronomers around the world, we're just okay, how do we do this? And kind of every time that people will come up with new idea to use the telescope, and we're just constantly being blown away with the new data we have. So here's the point. I'm going to tell you some of the latest results related to the ice journey that I mentioned in the kind of first 1/3 of the talk. So I think I made a version of these slides a couple years ago, and this is a title that I wrote, how do we really plan to use the telescope? But now we're not planning, we're using it, so how do we actually use this telescope? So again, this is my little baby protostar, and with JWST, there's a capability that allows us to see, kind of point the telescope into the very, very center when the star is forming, and accreting material, the gas is falling onto the star. And we actually have these kind of MASH-like instruments where we can take a spectrum for each single blocks, each single squares in this kind of in these regions. And so with a single shot, we kind of know the composition of the we not just know, we don't really just get an image, but we know the composition through the absorption spectrum that I show you like this. And so for each point, we can tell what's the chemical composition, the ice composition at that region. So this is really powerful instruments that really, I'm sure there will be more results coming out other than the one I'm showing you today. So one of the programs that I'm leading, we actually really fortunate to get some time on the telescope, and we were kind of awarded time to do 4 sources. Here I'm going to show you 1 sources because we only have 1 so far. The other 3 is going to be done in the next couple months. So maybe I'll come back some month later and show you the remaining results. But for this one, we're looking into this like dark patch of this Lupus cloud, and there's a star forming in there. And this is the spectrum we have toward those single point. You can see that again. That the line here is like super thin. That's how I plot it, because that's the way we can actually show the quality of the data that we have, the error that we have, or the noise we're getting from the instrument is super small compared to everything that's being plotted here. And you can see there's a lot of absorption dips, different dips with different shapes. There's also like a dips, like this absorption profile has some structure here. There may be some structure here as well, and all of this is telling us it actually have a wide range of different molecules that in this source. And we're actually thinking we're seeing a little bit more complex molecule, although we haven't been able to rigorously confirm it yet. But I will show you in a couple of slides about what's the latest on that. And one thing I want to bring up is that you can see that lines sort of like spectrum look a little bit thick here. Maybe you say, oh, this is noise, but no, they're not noise. They're just emission line, kind of like tiny spacing. These are all water lines, so these are the water vapors and CO, carbon monoxide gas around the protostar. So this is how much of a sensitivity we're getting from these new telescopes that we recently have the privilege to actually use it. So just as a contrast, showing that what it was before and how far we have come. So showing here is, again, the blue is the same spectrum I showed in the previous slides. The orange here, the data we have from a previous telescope operating the same wavelength. You can see that, for this deep feature, maybe you can see, okay, I can tell there's a feature here, but the amount of detail is just like so far away, like order of magnitude difference. And these like shallow features we can easily detect with JWST, but with previous telescopes, just like maybe they're there, but you couldn't really say more than that. So this is also like highlighting how far we have come so far, and also looking forward to how much more science we can get, science result and understanding we can get from the chemical composition of ice around a newly formed star. And another way people can use this telescope is not just looking to the protostar itself. So I mentioned like we can use point our telescope to the star, getting the absorption through the ice along a line of sight, basically between the telescope and the protostar, and we say, okay, how much of ice is in there? Another way we can use this kind of similar technique is we can pick the star in the background of this source. So this is my protostar, and like this. And the advantage of this kind of method is that, okay, you can actually probe the chemical composition, a different part of this, surrounding blob of gas around this, the newly formed star, and you can really resolve, to see how the chemistry actually evolve as function of position and also time, and perhaps also its physical conditions. And this has been really, really challenging because, the star is faint, and you're also going through a lot of matter in between. So recently, there's Ice Age program for JWST. They actually observe two background star that was very high extinction. Basically, there's a lot of material between us and those background star, and we're able to see again, a lot of feature here. Here's a slightly different wavelengths, but we still see methanol, water, CO2. And these kind of data is just something that we just couldn't do it before. So here's another number for comparison. JWST has about 100 times sensitivities than the previous instruments we have, which that means is that if we use JWST to look at one source for 1 second, with previous instrument it needs 10,000 seconds. So that's just the amount of a difference we're getting. So a lot of times we're joking among ourselves saying that, well, all of the sources we know already, they are all too bright for this new telescope because it's just so sensitive. Right, so going back to the complex molecular ice that I showed you, we actually, so these are two little dips, like shallow dips that I showed you before, like here, and we think they are very likely to be a feature of ethanol, which is like this is like alcohol we are having right now, and also acetaldehyde, which is a CH3CHO molecules, and could correspond to these two dips. Although chemistry is a little bit more difficult, solving the vibration is a little bit difficult. So we're still in the process of make sure that we can say for a good confidence that this is actually a feature that we see that can correspond to those molecules. But within it is likely to be those molecules. Again, like the Ice Age team, they also through very similar exercise, they also feel like the data they have, the dips they have here, also could indicate the same molecules like ethanol, basic alcohol, and acetaldehyde could actually appear like they're probing those molecules as well in the ice phase. So this is also very recent results. I think it's coming out in press release a couple of days ago. But this is also a new James Webb result showing this is a planet, exoplanet, a planet outside of our solar system. I think I forgot the name. VHS something. Yeah, VHS 1256b. I'm not expecting any of you know this. But here you can also see some dips here, right? So those are the dips I was talking about. These are looking into the gas composition in the atmosphere of those planets. So we can actually probe the gas composition in a planet outside of a solar system. I don't know how far away. It's definitely far enough so that we couldn't get there in time. So we also see, a lot of dips here. This is like narrower dips. Those are the gas phase absorption line we're seeing. So you have water, CO, methane, all kind of things. So we can use that actually to understand what kind of atmosphere they have. Is the atmosphere suitable for life or something? Or all of the things we want to explore through the planetary chemistry. So what's that? So we're expecting the other three sources. So this bottom left is the one we have. We have the other four sources. So just a little bit about how we design our experiments. So we want to look into the protostar, the baby star, that actually have rich, a lot of complex molecules in gas phase. And so we want to know, like, okay, we see them in gas. Are they actually coming from the ice? So the top two protostar are the sources. We know there's a lot of a complex molecule in the ice, and we're going to use JWST to see is there also a lot of ice, complex molecule in ice as well. And the bottom two sources, actually, what we pick those two sources because they don't really have a lot of gas phase complex molecules. We don't see them in gas. So what happened? Are they just not have those molecule form, or they're still remaining in the ice, but maybe they are not hot enough so that we don't see them in the gas. So these sort of like a little bit more in detail about how we go to design this experiment. So hopefully we'll get a little bit more holistic view about the kind of interplay between ice and gas chemistry happening in the early stages of star formation. So in the end, I just want to highlight two main messages right now. So it's very likely that the seed of our chemical complexity actually already been planted when the star just formed, and everything kind of like evolved from there through millions of time. And JWST right now is really unveiling the universe that we never been able to see before. And I think the coming decades, in the coming 10 to 20 years, we're gonna be at least part of astronomy going to be dominating by JWST, and just like we'll be constant in all of the new observation results we have so far. So thank you everyone, and happy to answer any questions.
Thank you so much. That was a lot of things to actually, and it's also very exciting to be a part of such a big mission.
Yeah.
And you all are saying some of the things for the first time. Very exciting. Okay, questions. Let's start from here.
Yes, so by the way the chemical molecules are related, distance or gravity-wise, the telescope, can it predict how the universe is going to grow or to shrink?
Yeah, so another part that I don't get to talk about, which mainly because feel like I'm not the right person to talk about it, but one main thing that telescope is set to do is to see the first generation of a galaxy, which we have seen. You know, I think we use redshift as a kind of parameter to say how old it is, or not how old it is, how young the source is. So we actually, you know, we're blown away with the previous redshift, like, I don't know, 7 or 6 is like really high, but now we're like redshift 20. So so they are already seeing a lot of galaxies in a, like, when the universe literally just born. And so that, I believe, what they aim to do is use the property of those galaxies, like how massive they are, you know, how bright they are, to actually constrain the fundamental cosmological model, like, you know, universe expansion and everything. So I don't know too much of the detail, but I know this is one of the major part of the research that JWST is doing.
Let's go ahead.
It's not really a question, but something I find interesting about your lecture is with the ice and heat to the universe. Are you familiar with Viking mythology at all?
No.
So Vikings believe that there's 9 realms of existence, and the first 2 are Muspelheim and Niflheim. One is completely lava, the other is completely ice. And why this is relevant to what you're saying is they believe life started when the first embers shot from the lava to the ice, which created gases. And so it's just an interesting parallel that, you know, such old, you know, barbaric way of life could come up with, you know, the same scientific analogy to what we're talking about today.
Yeah, and also, like, I think the fire we're talking here is, like, you know, luminosity giving out by the protostar. It's not just like sublimating the ice as only. They also could alter the ice structure. You know, ice is not homogeneous. I mean, you will form water ice first, and you probably form seal ice later. But then, or you have some mixture or something. But then you have heat coming up. Maybe the ice layer form in the bottom and come out quickly or something. And there's a lot of things you can do through the heating process. So yeah, I think that's really interesting. Maybe I should learn more on Viking mythology in the future.
Yeah. You had a question?
Hey, thank you for the discussion. My question, I guess, centers more around, like, getting the time on the telescope. What's that process like? And, like, how many entities are competing for that?
Yeah, very good question.
Lottery.
Very to my heart question. So the typical, it's a general concept. Telescope, you know, require a lot of effort to build. So oftentimes they want to attract the best, you know, scientists, best scientific idea to be used in the telescope. Therefore, you know, they're making the biggest impact possible. So oftentimes they would open to everyone to propose. I mean, you don't really actually need to be affiliated with, you know, a university or something. If you have a good enough idea, and you demonstrate, you know, basically sometimes we'll write a few pages of a document as a proposal. If they'll review those proposals, saying, okay, this is a sound idea, and this is an important scientific question, and your design for your observation that actually could lead to the discovery you intended to do, and they'll say, okay, we'll take this. But in reality, it's a little bit complicated because, you know, this is a new telescope. You know, we know how much capability it can do, so you will attract a lot of proposal coming in. So just as so they will announce that we're accepting proposal right now, and everyone submitted. Typically, that happens every year. So the last one, the most recent one, happened in end of January, and here's some stats. I think there are 1,600 proposals being submitted around the world. I forgot what's the total hours being requested on a telescope, but I know there's like 1 in 7 chance to getting the time. So, you know, you can probably spend, you know, a month developing your proposal, but you only have, I don't know what, like 15% of chance of getting time, which is not very high. Yeah, but people keep trying. You know, you want to use this new instrument, and I can imagine this competitive ratio, which is keeping up, well, going up probably for the next couple of years, and until it stabilizes. Yeah, so it is a nerve-wracking process, but it's really fortunate to be able to, you know, get some time, be part of it, and actually getting to see some of the data firsthand.
I had a question a little bit related to that. So, what it's like to use JWST? That is, do you just send coordinates and time and maybe the zoom to to tell what kind of image you're gonna get? How many parameters or things do you have to send as an input? And what are the outputs like? What are the formats? Or?
Sure. We as observer, we kind of touch some part of it, but eventually the observatory will take the parameters we give to them to actually, send. They are the ones send a comment to the telescope. They don't want us to do that. I mean, I'm not confident enough to use a $10 billion instrument. But from our side, what we do is, well, first we check if our source, what we want to do, the signature we expect, how bright it is, can actually be detected by the telescope, right? I mean, that's first line of argument we want to make, is it actually doable? But then there's other thing we want to check, like maybe our source is too bright. Sometimes the CCD will saturate, and we need to justify, is that going to be a problem or not? Is there going to be, sometimes the source is too bright, it will actually damage the instrument, right? So that's something we need to know. And also we need to know what kind of mode. There's probably like 20 different instrument mode we can choose from, and you need to choose the one you actually want to use, and to actually be able to justify why that mode you're going to use. And so we kind of need to know to some extent how the instrument, how the detectors actually works, so that we don't actually use the telescope in some dumb way and actually getting crappy data in the end or something like that. But I would say most of the technical part is the observatory is taking that responsibility to actually maintain a telescope and send comments. And what happened is that there's like a software that they develop. We can setting up our observation as a whole, and it will through some validation process, of course. It will just be put in the queue for a telescope. So the telescope basically will develop a yearly plan. It's like, okay, we're probably going to do your project around this time. We get a range of time, and when the time is closed, they will say, okay, your observation is scheduled by this hour to that hour. And it's a space-based telescope, so often you don't really have a weather issue. So most of the time you'll get your scheduled observation executed, and then they will run through their pipeline to process the data, and you will get a data back. So there's another interesting point about space-based observation is you have to download your data. You don't have cable there. So a lot of time, how much data you can take per day is actually limited by how much data you can download from the space. If you cannot download it, you are not getting the data, regardless how much data you've taken. So there's this kind of tricky part. You cannot just say, well, we're just going to take as much data as possible. No, because you don't have the technology to actually get the data back. And so that's something that oftentimes we'll also face that limitation as well in observation.
I guess I would be very curious how much data the JWST store at that telescope.
They don't really. I don't think they store it, because if you need to store, they probably want temporary storage, but it doesn't. They shouldn't have something which is we're going to store it and we're going to retrieve it in some days, because we're not going to be able to do that. I think we can download either 24 or 48 gigabyte per day. I think that's the limit. That's basically through the deep space network. So there's very limited amount of time you can do. So they have to design their instrument to be really efficient. They will have to do some hardware averaging or something. You cannot really record every single seconds of data you're taking. There's probably some crude processing already happen in the hardware level, and you're getting somewhat combined data in the end. That's why it takes $10 billion.
Any other questions from this side? Yes?
So this is not a technical question because I'm not a researcher. So considering that you're the very few person who ever use JWST, and you're the first person I've ever met in Japan, I would just want to know what do you imagine to be the most exciting discovery that JWST will uncover in the future? Just imagine. What do you think will be the most exciting? What can we discover?
Very good question. So my research is kind of more in line with star and planet formation. So I personally found those exoplanet atmosphere studies really interesting. I think the spectroscopy perspective of JWST it's probably not as appealing as it should be. Sorry, it's not as appealing as it appears because they're just spectrum. They're not. We don't really produce pretty pictures, but be able to understanding the atmospheric composition, whether it is oxygen rich or CO rich or has a lot of clouds. Sometimes you can use that to infer what's the cloud structure in those planets. Do you have a thick cloud like Venus, or do you have like Earth-like atmosphere? And potentially, and I think we'll get there. We're getting some atmosphere composition that is very similar to our Earth. And at that point, I think there will definitely be people say, let's go there. But we'll see how feasible it is at that point. But yeah, I think exoplanet atmosphere characterization is probably, it requires phenomenal, unprecedented sensitivities and spectral capability that James Webb is built for. Also, something I wasn't. Oh, there's another thing that's really cool that has already been seen, but I just want to say it. There's like a gravitational lensing effect, which basically the light passing through a massive object, the light will get curved, and you will see a very distant object. And so as a kind of just like general concept, we call it high redshift galaxy, or like the noon time of cosmic evolution is about redshift 2. The redshift is higher, meaning early stage. And we recently see a star, a lens star, is in redshift 4-ish or something. And in image, you can actually see a trail of dot on your image. And those are like starlight got lens in different angle or something. That was just like, what? Like, can we see? It just, I don't have the image right now, but it's just phenomenal. Like, I never imagined we can see that. So it's just really cool.
Yes.
Short question. What would be the most promising biosignature or techno signature in the emission lines, you think? Because they comes from the atmosphere, right? So what kind of composition is more promising?
Well, I'm probably not the right person to answer this, but I would probably say some carbon-based molecules, like methane, probably. Obviously water and oxygen will be pretty big. I don't know if we will be able to see more than that, simple molecules. To see, if we can see complex molecule, like I'm showing you, in exoplanet atmosphere, that will be like bunkers. Like, I don't think so. But no, I don't know whether this. The short answer is I don't know. But I think, and my hunch will be there's no single signatures we can use, and everything has to kind of be assisted by some sort of modeling as well, and retrieval technique for the atmosphere composition. We're definitely not going to be able to see. Well, maybe, but I think it's very unlikely we'll see technical signature directly. Maybe we can infer in some way. But who knows? We're still in a very early stage of using these telescopes. People find really creative way to use Hubble after 30 years, so yeah. We don't know.
All right. Chase?
Yes, actual question this time. Can the James Webb Telescope see the Andromeda system?
Yes. And I'm sure someone's taking a picture of that. And I think for maybe for Andromeda, we can probably see individual, protostar in Andromeda or something like that. I'm like somewhat confident that we can do that. Yeah.
Okay, last question.
So will the telescope be able to see thousands and thousands of planets, chemical compositions, and from that analyze, is it likely that life is on that planet?
Yes, for most part of that question, maybe not the thousands part, because it costs a lot of time. So I don't know what that BHS 1296b planet, how much time it takes. I'm guessing on the order of a few tens of hours. So we don't have. It's unlikely to think we'll have 10,000 hours or like a couple tens of thousand hours spending on just do exoplanet characterization. Maybe we'll get there at some point, but I think the remaining of those collections, yes, I think we will be able to do that.
Great. Thank you so much for questions.
Thank
and
you.
also thanks for the great talk.
Yeah.
And you'll be sticking around?
Yeah, I'll be sticking around. Yeah.
And I just also noticed you have a
Yeah.
really cool collar pen
Yeah.
of JWST.
Yes.
Very cool.
All
Thank you
right,
so much.
Thank you. All right. Do you want me to?
Oh yeah, can you?
Sure. Excuse me.